Thank you so much, Abhishek. Uh, yeah, I'm kind of missing Yuval in the audience. Uh, Fun fact, I mean, he's amazing. He comes up with these great discussion points. I don't know if you have met him. Like, he's just too much information content when he, talks to people. Uh, and when he invited me, he's like, Ayush, I'm going to behave. Uh, I didn't know the definition means absence. Yeah, but jokes apart, he's like a mentor-like figure to me. So it was all like, what I meant. Anyway, so Amit gave a talk just now on obfuscation, and it is really giving a high-level landscape of how things work. I'm trying to go into the little bit of a weaves into how the construction works, and the talk will be mostly like a tutorial style of talk. As you can see, these are handwritten slides. So the good news is that we can set up our own agenda essentially as we go. So you guys are responsible to stop me and ask as many questions as you want, because I mean, everyone is from a different set of technical understanding of this topic, and maybe one question can help others. Um, yeah, that's all I wanted to say. The downside is that you have to put up with my handwriting. Okay, so let's begin. I'm going to be talking about this theorem, and you saw this when Amit presented it. I'm going to show how you can build indistinguishability obfuscation assuming sub-exponential hardness security of three assumptions: PRGs and NC0, expanding, let's say, n bits to n to the 1 plus epsilon, where epsilon is a tiny constant, barely expanding to like a polynomial amount. Then LPN over large fields. This is also what Amit mentioned. The error rate I'm going to use is small inverse polynomial in the dimension, 1 by L to the delta. Delta is arbitrarily small constant greater than 0. So yeah, it's still, we don't know PKE from this, so it's still sort of a conservative regime. And third is essentially bilinear maps. You can instantiate this assumption with like different sort of bilinear map assumptions like SXDH and all these kind of assumptions. For concreteness, DLIN is an assumption that we can use. If you're willing to assume just polynomial hardness of the same, you can get functional encryption, which is also a really cool notion, I mean, precursor to obfuscation. Okay, so this is the theorem that I'm going to, going to weeds off. How are you going to construct obfuscation? I want to mention that we had a previous paper, which was in 2021 at Stock, where we had learning with errors additionally, aside from all these three assumptions. And this paper in particular gets rid of learning with errors. So I'm going to kind of focus on why learning with errors was at that point seemed kind of inherent, but then we were able to kind of remove learning with errors from this list. Not only because there were interesting techniques, which at that point I found really surprising. It is also that it leads to surprising implications. So in particular, basically, you can essentially base most primitives that you can build from obfuscation without LWE, essentially. So bilinear map world is essentially as powerful as LWE. That's kind of the takeaway message. And in particular, homomorphic encryption. I know people have tried building homomorphic encryption. Right now, the only game in town for at least semi-practical construction seems to be LWE. And yeah, what our theorem at that point implied was that, well, you can, if you have bilinear maps, you can essentially get super impractical. I mean, if LWE-based construction is impractical, then this is like orders of magnitude impractical. Okay, so what I'm going to do now is basically try to fill black holes that left in Amit's talk with more details. I'm going to focus on first motivating why LWE seemed inherent, and then show maybe one or two cool ideas to get rid of them. Okay, and my hope is that this tutorial helps at least. Yeah, I want students to work on it. Okay, so how do you build obfuscation? Turns out that there's only one game in town. I mean, there's only one great bootstrapping theorem. What does it, I mean, this is due to Anant and Jain, and Abhishek is in the audience. And then Bitensky and Vakanathan. What they showed is that in order to build obfuscation, it turns out you need something seemingly much simpler than obfuscation. If you can build that, then you can build I/O. And what that thing was, it was functional encryption. You need some additional properties from functional encryption. So let's talk about function class first. And just to recall, functional encryption is a specialized form of encryption schemes where just having all or nothing access on the message, you can release functional keys which let you derive functional values, and just that. So the function class, you can actually get this sort of theorem from a variety of functional encryption schemes with like different kind of structural complexity. What we will be interested in are low depth circuits. I mean, I want to kind of come up with the simplest possible thing. So let's just try working with simplest possible circuit family. So I'm going to be working with circuits where the number of inputs are some n, which is, think of it as a varying polynomial in the security parameter. And then the number of outputs is slightly expanding, n to the 1 plus rho. Okay, so just slightly expanding. And then each output bit is computed by a very small circuit of size lambda, let's say. And these n and m are sort of large enough polynomials of n. Okay, so that's the function class. And the sublinear, what this means is that essentially the time it takes to encrypt should be better than computing the function itself, right? So it should be sublinear in the size of the function. So the way I stated is that the size of the encryption circuit, which computes the ciphertext, should be n plus something which grows smaller than the size of the circuit, m to the 1 plus epsilon. Okay, so AJ and BB showed that if you have these kind of properties in a functional encryption scheme, then it already implies obfuscation, and this is a great news for us. Let's just focus on building, FE. So now I'm going to give you the blueprint or sort of structural. We didn't talk about how various components integrate. We will still not do it in this talk, but at least I want to give you a very, very high-level skeleton, which, I mean, for this part of the talk, you could think of it as being, as long as you just understand the world picture, that's great. I'll be focusing on what I think are the most conceptual part of the construction. So here is what the JLS21, the first paper. Daniel?
So, so you said that using these assumptions with the sub-exponential
loss
harness, you can get I/O.
Yes.
You also said that from compact functional encryption, you can get I/O. You also said that from polynomial version of this assumption, you can
get FE.
Encryption. So what's the gap?
Then if you have polynomial hardness, then you get FE. If you have sub-exponential hardness, you get sub-exponentially secure FE. And sub-exponentially secure FE implies I/O. If these assumptions are sub-exponentially hard, then the FE itself turns out. Okay, so how does the lay of the land look like? Well, basically, what you want to do, you want to kind of evaluate, like obfuscate a circuit. And to an evaluator's perspective, it involves securely computing a function without leaking information. So you need a functionality enabling primitive. There's many ways to do it. But in that paper, we used sort of a specialized homomorphic encryption. I'm not going to define what this means, but this is a homomorphic encryption which is sort of capable of computing arbitrary polynomial depth circuits. Okay, so we use that. Now we kind of have to decrypt this somehow, but we want to decrypt it like securely. So we need to kind of enforce this, and that's where two other tools come into being. First is a notion called partially hiding functional encryption. And this is a very nice abstraction, which Amit talked about. This is the functional encryption, the best possible form that is currently available to us by means of bilinear maps. Okay, bilinear groups are nice, and like those allow you to do degree 2 computations. The best possible functional encryption that you can hope, best possible in some sense, is this notion called partially hiding functional encryption. And what's so special about this is that it allows you to encrypt vectors over the group order of the group. So you can encrypt vector which is partitioned as two components. One component is public, the other component is you're intending to hide. And the function class that it supports is that you can compute pretty much anything over the public component. By anything, I mean sufficiently large constant degree polynomials, the computation on the secret part has to be restricted because bilinear maps can only go thus far. It can only compute degree 2 functions. How to build this, I won't cover, but Hoytek has a beautiful paper on this, and it's a very nicely written paper. So you should totally read that paper. Okay, so once you have this, then the other component is that, so you have this homomorphic encryption, and now you kind of have to enforce that the adversary or the evaluator is able to only compute the function that I intended the adversary to compute, and that's where this thing comes into being. But then you need to decrypt it securely. In degree 2 polynomial, you can decrypt like FHE. So what you do is you go for a proxy. That's where you have to add a noise. The noise is generated by a degree, like a PHFE friendly PRG, and that's called a structured seed PRG. Okay, so this is a PRG that you can implement in securely using PHFE, and then that's it. Okay, yeah, that was a long spiel on this. I won't expect you to kind of remember this throughout the talk. I'm going to only focus on certain parts. I just want to kind of give you how things look like. In terms of assumptions-wise, this was using LWE. Amit showed how to exactly do from LPN and PRGs in NC0. Well, he didn't quite show it. I'm going to kind of spell it out clearly. The third thing is PHFE, which you obviously know from Balian maps, and that is where we are at. And then you have kind of a routine step combining these. Really, it's just like there's nothing there except pattern matching. Once you have the definition, you can kind of combine them. And it gives rise to a functional encryption scheme, which I'm calling for this purpose of the talk, functional encryption star. Now, what does star mean? Well, star means that essentially almost takes us there. The size of the ciphertext that I'll be interested in will be sublinear in the output of the output length or the circuit size that I'm interested in computing. The downside is that the encryption time will not be. Encryption time will still be linear in the size of the circuit. Okay. If you recall what Amit was doing in his talk, there was this LPN part. We're computing some polynomials, and then we had to compute this, matrix which had sparse entries corresponding to the error of the computation, and then you were compressing it. That time, maybe the description is small. Computing it won't be efficient. Okay, so you have to still deal with this issue. Luckily, there's another beautiful paper by LPST. Rafael is a co-author. And yeah, it's a beautiful paper. And what it showed is that using LWE again here, you can kind of circumvent this issue, and you get sublinearly compact FE. Again, I won't talk about it because we kind of, in the later paper, showed that this is all redundant. I'm just trying to show at this point where LWE came. So what are the issues? The first issue is that LWE comes in like the construction itself because we need homomorphic encryption. The second issue is that we need to upgrade sort of a FE where it's FE star. It's not FE. That's where the second construction comes in. So that's what I'm going to show how to deal with. Well, first thing is that we got to rid of the homomorphic encryption. We can't use it, or at least in the full generality. The second is that there is this inherent issue of this matrix compression, which is not sublinear time, or it's not efficient the way I want it to be. So if you inspect, again, it boils down to this notion that we saw, which is, I'm going to call it structured seed PRG, and again, I'm going to formally define it. So this is the notion where that was inherent, so kind of have to deal with that too. Turns out the first problem is really easy to deal with. Those in the know that there is another functionality enabling primitive called garbling, and in fancy words, we call it randomized encoding in NC0. What are these? This is just Yao's garble circuit, but instantiated with, we use symmetric encryption to do garbling, instantiated with PRGs in NC0. The whole thing becomes NC0. Every garble gate table can be computed as a constant degree polynomial in the circuit input and the, well, not the circuit, but input and the randomness at least. Okay, so uh, that's another way in which we can kind of get functionality. And yeah, so once we have this, then we can kind of, um, instead of constructing something which was evaluating PRGs, I could instead evaluate this. And this is exactly what Amit was talking about. We are going to compute this, and that gets rid of FHE. So in fact, Amit already talked about how to get rid of the first issue. I'll be focusing on the second issue because that's where I feel more interesting stuff is going on. Okay, and rest of it is like given prior work is just pattern matching. So let me kind of remind you quickly the definition, just so that we have like formal. I mean, you've already seen what we're trying to do, but just it's good to write down a definition because it gives you some sort of clarity. Good. So what are we trying to do? I'm going to define the notion of time succinct SPRG. What's this? So there's a setup algorithm. Essentially gives rise to two vectors, P and S. P always means public, S always means secret. Think of them as vectors over ZP star, where you're working with order of the bilinear group, and that's where P comes in. The first property I want is that the size of these seeds are smaller than the length of the outputs. Yeah. The next thing, what I would want from this is security. I should be able to evaluate on this pseudo-random generator so that given P and this evaluation, all it looks like is P and truly uniform random string, okay? And third is what makes it really useful for obfuscation or PHFE friendly is that this function which evaluates this PRG should be computable by a bilinear map or PHFE. So it should be computable as a polynomial over ZP of constant degree, some large enough constant. And its degree should be just 2 in the secret component. Okay. And by the way, just to not have to say this over and over again, constant degree over P and like degree 2 over S, I'm just going to call it degree 2.5. Okay. That's the convention. Okay. Let me now talk about the really crucial property, which is essential to get rid of LWE. The property that I need is that the time that it takes to set up this, not just the output size, should be smaller than the number of random bits that I'm extracting. How small? Like polynomial small. M to the 1 plus minus epsilon. For even a tiny epsilon will do. Okay. And yeah, I'm going to, for the most part, just ignore poly lambda log P factors. Okay, so that's time succinct SPRG. Now, Amit, in his previous talk, he was describing under the hood how this SPRG construction looks like. Turns out it doesn't satisfy time succinctness, and that's kind of inherent reason why we needed LWE previously. But I'm going to tell you how exactly that works, and then what exactly was the reason why it seemed hard at that point. Okay, so here's the construction. Obviously, you need to extract random bits. You need to work with a Boolean PRG, and we're going to work with a Boolean PRG in NC0. So constant depth, computable, local random functions. Okay, if these PRG expanding from n to some polynomial in n were degree 2 over ZP, then I would have been done, right? Nothing to do. The problem is you can't design local functions which are degree 2. Okay, local pseudo-random functions. I mean, if it's degree 2, it's going to be broken. Okay, it turns out this is a characterization of local functions and just impossible to build it. So what do we want to do? Kind of squash its degree down to make it PHFE friendly so that we can evaluate it using bilinear map. So this is the idea that Amit described. So here's what I'm going to do. I take a random seed for this PRG, okay, and then I'm going to encode it as an LPN sample, like using an LPN sample. So AI inner product S plus error plus xi. Okay, this secret is much smaller in dimension compared to the length of the seed or whatever you will. So I'm going to assume that it's dimension k, much smaller. Why this helps, we'll see it in a minute. But what's the goal? Um, oh, by the way, the error probability is kept sufficiently low so that I can eventually get some sort of compression. So why does it help? I'm going to come to that. But for the time being, what do we want to do? We want to come up with another secret seed such that it's small and that you should be able to compute PRG using degree 2.5 computation over PNS. Okay. So first thing which I want to say is that for security, if you assume that we already did this, we are able to come up with the seed, which I haven't told you how, then security, by the way, trivially holds because the security notion says that P and evaluation should look indistinguishable to random. Is this true? It's true because P is just LP and sample encrypting the PRG seed, and this is just PRG evaluation on X. So first you can replace or switch this with pseudorandom, and that's going to hide your PRG seed, and then you can switch PRG's evaluation to random. So security, I won't even talk about for the most part of this talk. It's all trivial. Good. So how do we compute S? And it's not that hard. Well, first intuition is to look at this LPN sample. It's encoded with a very small secret, with very small dimension. So a natural thing is that I think about my computation. It's a very local polynomial. Let's say it's degree D. Okay, D is some tiny constant, or whatever PRGs and NC0 give you. So the first natural thing is that why don't I tensor all powers of S and give out all the monomials in S1 to of degree D, and that's my seed, the secret seed. Why is this reasonable to do? Well, because if you examine this G, E minus S times A, which is, look at this polynomial, turns out it's just G X plus error. Error and X is remaining, so that's the only thing. So you can compute this. This polynomial is nice. It's degree 1 in its degree D overall, and it's degree D in P. But if you think about its degree in this component, it's actually 1, right? Because the whole thing is degree D. Okay, but then yeah. So this is already good because we have won half the battle, right? G is local, and error is like really sparse. And therefore, on most of the coordinates, typically it will happen that the errors are 0. So what you get at the end is that for most indices of the PRG output, you're going to be right with probability all but 1 minus k to the minus delta or something like that. So you accept m times k to the minus delta evaluation outputs, everything is correctly evaluated. Okay. So now what do? We are able to correct something which is compute something which is almost there. Let's correct it all the way. I'm going to look at this matrix, Gx minus Gx plus E, and sort of compress it so that it can be reconstructed back in a degree 2 operations. So this part is already computed. This part, well, we need to account for this. So the first, the idea is that why don't I just look at this matrix, run over all the output bits, and just compute this matrix? So that's step 1. It's going to be very sparse. How sparse is it? It has m times k to the minus delta entries, little less than m. The second idea is that if I partition this block into chunks or submatrices, where every submatrix is of size k to the 1 minus delta, then, k to the delta, then every entry is going to have, like every submatrix is going to have, with high probability, O tilde of 1 or polylog number of entries. And then at that point, the matrix becomes very low rank, and then you can kind of factor that. So look at every submatrix and then just factor them. Okay. Good. So now all the checkboxes are satisfied. The size of this, the circuit size to compute this is n times k because you're computing these inner products. The size it takes to compute S0, which was the power of S to the D. this is k to the d, k is the dimension. This is still sublinear in M because I'm assuming that this is much smaller than M. What about size of S1? Well, naively, it's going to be M. Okay. Why is it M? Okay, this boils down to a really simple.
S1 is the error vector.
Huh?
S1 is the ERR vector.
Yeah, the S1 is a compression of the the error locations, the matrix M. Good. So why is it taking M time? Well, first, I don't know a conclusive answer to this question. Can't rule it out. Can't rule out a construction conclusively. That said, I believe that it's going to be hard to examine this construction and make it sublinear. For a simple fact that the monomials that you're evaluating in this PRG completely unstructured. The error locations are completely unstructured. They arise at very random locations. And then think of this task where you have this matrix and you're, let's say, even putting one cross in this matrix. That itself leads you to kind of read every entry. And it's going to take M time to kind of write stuff in this. Okay, so this might seem like inherent, and that's what I was telling you about. Like I found this really surprising that we were able to deal with this. Okay, so what do? We take we just think about this really. I mean, the spark on this direction came from just simple observation. If you had an ideal world, like a world where you were trying to design PRGs where RAM time is sublinear, but that you could do. I'm not going to spell out the details here, but imagine if I'm able to store all the non-zero locations in a tabularized way, and like all the monomials that every input is connected to, there's a way to kind of make this work out in sublinear RAM time. Okay, but how do we do it really here? Yeah, we don't know actually how to do it. However, this is where, well, yeah, we kind of went after a slightly contrived abstraction, which we call pre-processing polynomial encoding. This is a contrived abstraction because in the first glance, it won't be even clear why this is useful to do. But then, yeah, with crypto magic, we are able to show that it's still useful. And then here we are able to show sublinearity. So let me tell you the task, and it's really intuitive. So what's the task? Now in this game, as opposed to working with one input and computing M outputs, I'm going to think of an amortized version of this task. I will have like k input vectors as opposed to one, x1 through xk. And then I'll be interested in computing, say, m degree d monomials on all of those k inputs. Okay. So in particular, I'm interested in computing m times k monomials as opposed to m, because there are k inputs and then m monomials. So it turns out when you have the same set of m monomials being evaluated for k inputs over and over, you can kind of roughly amortize away. You can effectively simulate the properties of an efficient RAM program for a simple task. And I'm going to show you, just depending on the time, maybe I'm going to give you a high-level idea, maybe I'm going to go into more details. But yeah, that's my plan for right now. Okay, so let me try to formally define the task, and then we can think about it. So here's the problem. Now, as opposed to, this notion, pre-processing polynomial encoding, the task is that now I'm going to have a setup operation, which will take these k inputs. Of course, at the end of the day, we would want to hide these inputs. It will also take m monomials that you're interested in computing for everything. What does this setup operation do? It outputs this, again, public part of the seed, private part of the seed. Then there is an evaluation operation, which takes these, whatever monomial you're interested in for whatever input, and it takes the seed, and it computes the monomial on that input. What I want is that, again, as before, this should be degree 2.5 computable. Okay, now my sublinearity game has changed. It's no longer being sublinear in M. It's going to be sublinear in M times K. Okay, so what is the kind of expression that we are okay with? So things like K to the O of 1 is okay, because we can parameter hack and make things sublinear. Even if it's K to the 10, it's perfect. Then things like N times K cube n is the number of inputs, k is the amortization parameter. This is also okay. It should not be bigger than m times k. So it's okay to have terms like m to the 1 minus epsilon times k. It's also okay to have terms like m times k to the power 1 minus rho. Okay. Great. So indeed, that's what we do. We design a PPE, reprocessing polynomial encoding, where the efficiency to compute it is this much, and this turns out to be useful. Okay. In fact, here I want to stress that when you look at this term, m times k to the 1 minus rho, think of it like saving a little bit for every monomial. That's what we are doing, and this turns out to be useful. Okay, so let me show you how it's useful. Well, it's going to give rise to time succinct structured CPRG already. Why? The idea is that you can use PP to compute a PRG, which uses the PRG in NC0 and outputs bit to n to the 1 plus epsilon output bits. And by the way, since it's local, the number of monomials is still like order of the number of output bits. So we're going to compute this PRG, which samples k different seeds and then outputs all of them, g of x1 through g of xk. And this is itself a PRG, right? It expands n times k to m prime times k. But due to PPE, our time to compute it is sublinear in this. So while we were stuck at that abstraction, if you use this kind of notion, then we're kind of unstuck. And this is the core property that we were trying to use in this setting. So why does amortization help? I'm going to give you a short answer, and then if time permits, a long answer. Let's think about short answer because I think it's really cool. So it turns out when you have a very simple RAM task and you want to do it over and over, it's really surprising that you can often do away with, you can amortize away the effect of it being a RAM program. Not every time, but at least in many different settings. So let me tell you how. So consider this. By the way, this is a math puzzle. We are nothing to do with I/O. So with this task, we have this circuit C, which we want to design. What should this circuit do? It takes an input, a database, n-dimensional vector. N is very large. And then it asks queries. It takes in some queries, I1 through IQ. And what it wants to do is basically output the value of the database at those locations. Okay, really easy. So it's a lookup task. When you implement it as a Boolean circuit in the usual sense, what do you expect should be the size? Like, what's the size that you could think of in this setting? Anyone who hasn't read the paper can take a guess. Q log n. How? So even for one query, you got to read everything, right? So it has to be at least n. And then it has to be at least q because you got to process all the queries.
I'm not sure about the log factors, but O tilde of n plus q.
Yeah. Do you have a solution or guess?
Sort the i's into the database.
Yeah, good. So you're on the right track. So I won't spoil it for everyone. Okay. Yeah, but that's right. What's your name?
Lance.
Lance has the right answer. So it turns out that naively, if you try to do it, it's n times q, but there's a clever way which takes n plus q time. You don't have, for this solution, you don't have to be in 2025. You could do it when even 20, 30, 40 years ago. There are two ideas, and I'm not going to give citations because these works are just so classical. The first amazing result in TCS, which I'm going to use, is the fact that you can sort circuit by linear size circuits, right? You can sort arrays with linear size circuits. There's AKS sorting network, and there are lots and lots of work here. The second idea that I'm going to use is that when you look at Turing machines, let's say it has constant number of tapes. I give you a promise that this Turing machine actually runs in time TFN. Any such Turing machine computation can be simulated by a circuit of size which is quasi-linear in the time it takes to run the Turing machine. It's a complicated process. It goes through what's called as oblivious Turing machine. And yeah, don't even ask me how it works because I might not be able to recall. But yeah, this is something like this exists. And turns out these results are really, really useful in this setting. So here's what I'm going to do. This is my task. I want to come up with a small circuit. The first thing I'm going to do is that I'm going to just format this input. So you have I1 through IQ. I'm going to format it as 1, I1, 2, I2, so on and so forth. So all I change was the second half of the thing. This can be done in linear time or in Q because I'm just basically reading in on a Turing machine. The second thing which I'm going to do is sort this according to the second coordinate, I1 through IQ, which is what Lance was suggesting. And why is this efficient? Because sorting networks. Efficient. Quasi-linear, right. When I say linear, like even for most of IO research, we don't even talk about polylogs. And so ignore my sort of inconsistencies when I say O of 1, it actually means O tilde of 1, things like that. And sometimes when I say O tilde of 1, it might even mean depending on security parameter lambda, which is like blatant abuse of notation. Great, so you can sort it. But then once you sort it, then things are really, really nice. I've kind of sorted the indices that I want to look at in kind of ascending order. What do I do next? I read again, like on a Turing machine, and then just port over the values on the database. Again, linear pass, so quasi-linear time. And finally, when I'm already in the right format, I'm just going to sort them again according to the query indices, and then I'll get the right answer. Okay. So yeah, that's it. Turns out that's done. And this is all we need, actually. Many, many applications of these two ideas in order to pre-compute the seed and make it like sublinear time. But maybe what I'll do next, I'm going to just describe the construction, but I'm going to take a leap of faith and not go into formal weeds of how exactly things are sublinear. But I'm happy to talk offline, and because these are just details and don't want to go into super high level, super technical stuff. Okay, so how do you build sublinear processing for PP? How do you design PP? Remember, we have these inputs x1 through xk. You are interested in these monomials. The idea is that I'm going to, again, as before, the only thing I know how to do is basically for the public seed computation, I'm going to just encrypt all these inputs, the k times n components using LPN. So there are like n times k ciphertext, each with different coefficient. And again, I'm going to, for sake of my not having too many symbols, think of the dimension being the same as the amortization parameter. Okay, so this is already good. This is the public seed, that's it. This takes n times k square time to compute. So it's all like in our quota of sublinearity. Security is also trivial because all you need is to show that this is indistinguishable to random. Now, how do I sample the secret seed in time, which is sublinear in m times k? Let me just tell you what the seed is like, naive way of computing it. I mean, let me just tell you what we are computing, and then how I'm going to show how we can compute that in sublinear time. So what are we computing? As usual, the monomials I'm interested in are always degree d monomials. So the first thing you do is tensor the secret d times. This lets you compute degree d monomials approximately. So things like monomial on any input plus the error. But note that because the error is sparse, then this monomial is constant degree. So this can be computed with 1 minus order k to the minus delta probability correctly. Okay. What about the next thing? We wanted a correction matrix. Well, this is where the game changes. As opposed to computing one giant matrix where we are computing, we are compressing the error locations, I'm going to compute m different matrices, one for every monomial. Okay. So in particular, I'm going to compute m different matrices where every Lth matrix is only concerned with the monomial QL, but it lists down all the errors, which varies over the inputs j from 1 through k. Okay. Now it's not going to be m cross m matrix. This is a much smaller matrix of dimension k. The number of entries are k, so can be written as root k cross root k matrix. The next thing which I'm going to do is that I already observed that most of these guys are 0. How many of them are 0? I mean, all but k to the minus delta fraction. So the number of non-zero entries here are k to the 1 minus delta, which means that if I divide it into k to the 1 minus delta chunks, like that, each of the chunk is going to have order 1 or O tilde of 1 number of non-zero entries. And then I can compress as before. Good. So it's really straightforward. What I did was essentially just instead of working with one matrix, I computed like many of them, m of them, and each of the thing was slightly smaller. But I haven't told you why are we winning yet, and I'm going to do that in a bit. The point is that roughly what I'm going to show is that each of these things can roughly be computed in time k to the 1 minus delta over 2. So I'm going to win just slightly per monomial, and that's enough. Good. So just to kind of benchmark or check things out, the first step was very good, n times k squared. The second step was already good. It's k to the d. Now let's focus on the third part. The size is already good. It's m times k 1 minus delta over 2. We just want to see how can you compute it more, efficiently by a small circuit. And what I'm going to do next is not going to go into the weeds of how things work. Maybe I'll give you like super high level picture of how the circuit looks like. Well, the circuit is going to have 2 stages. The first stage is going to format this. So what's a master input? When you're encoding things, you have these X's and the errors that you're going to add at every sample. I'm going to store this. And then the first thing I do is kind of format this input in a way which makes it like nicer for me to use later on. And then I'm going to use it. So what's the first stage? In the first stage, I am going to, there are n input components for k different inputs. I'm going to break it down into n components. And every component, or every chunk here, will have only the list of non-zero, where the non-zero coordinates where you added error is listed according to the input index j, which goes from 1 to k. So in other words, what I did was for every input component, from 1 to n, I identified a list of non-zeros, the inputs input indices from 1 to k, which were non-zero, because these are the things which are going to cause problem later on. These are the things that kind of determine non-zero entries in the matrix, right? So I did that. And then what I'm going to do is come up with m different circuits, one for every monomial, but they're going to compute these little seeds, which are going to just compress the correction matrix for only that monomial. Good. So let's focus on the first stage and just kind of zip through really the main point. How can we quickly identify non-zero locations? Again, you use sorting networks, because non-zero is greater than 0, and you can have that partial ordering and then essentially sort. And then you can also, if you want, you can sort according to the index j here. So it's all linear time, n times k. Once you have identified the list of non-zeros, the rest is compressing this seed. Okay, so how do you do that? Well, best if I give you an example. Let's say we were interested in computing x1 times x2, really simple monomial. And I'm lucky enough that I have already pre-processed list of non-zeros that uh, in the input indices 1 through k, where I added errors. Now this monomial only depends on the first and the second component of every input, right? First step I do, and again, just to recall, all I want is this compression of this matrix. So what do I do next? Is that first thing I do is I kind of merge these in this form. Again, a linear pass on the Turing machine. Basically, what I want is that for every j, identify the value of x1 and x2 wherever there was an error. Okay. How much time does it take? Well, there's a merging operation. There's one more thing I kind of brushed under, which is that for some indices, index j, it is possible that there's a non-zero error component here, but the component doesn't exist here. Maybe that input was correct was not there in the second list. What do you do then? You kind of look up in you have the input matrix in the inputs x1 through xk. You can kind of do a lookup, but that can be amortized away. So I'm brushing at this detail. Okay, but once you have kind of merged these two, then computing these compression is actually really easy. You know exactly, and you exactly know which inputs are problematic inputs wherever there's a noise, and you know the values of x there, and you know the value of error there, and they are kind of already sorted in the right format. Instead of computing these low rank like computing the matrix first and then decomposing it in low rank factorization, you can kind of also implicitly come up with the factorization in the first place, because they're really low rank, like constant or O tilde 1 rank. So you can really essentially just read it in this low rank format. And that's that. Okay. Questions? Yeah, this is a bit of a technical stuff, but yeah, if there are questions, I can take them now. Maybe we should let the fire truck ask.
I got lost there. So see, you need to be able to compute. You don't have time to compute the whole error vector, right?
You don't have time, but you know the noisy locations, and they're kind of indexed according to where they fit in the matrix. So just read out like linearly. Let me give you an example. So suppose I want to put.
How do you know where the noise appears?
So I know like j that this is a problematic component, and I know the values. Right? Let's say I know it for one j, and I know that it sits at kind of this location, like somewhere. I don't know. So this is, let's say, T1, T2. So what I can do is basically give two vectors. Here I'm going to put it at T1 location, the correction value, and like 0 everywhere. So this is the correction value. F of x1, x2 minus f of x1, x2 plus error. And here I can just put 1 at the T2th location, right? I mean, I don't need to compress it. I can just implicitly compute all of them. That's the main point. Good. So now let's try to stitch things back. And at this point, what I'd like to do, basically make things slightly more concrete as opposed to abstract. And I'll try to give you a skeleton of how the functional encryption schemes looks like at the end. So first of all, we are not going to do this stuff for a PRG. Remember, my goal was to get rid of FHE there, and I wanted to work with randomized encoding. So we'll do the same thing. Instead, we're going to pre-process randomizing polynomials. So again, same syntax as before, but now the output should be some randomized encoding of CNX. Okay. This, can we design this primitive? Yeah, you'll need to use PPE that we just built, but then you need to use sufficiently structured randomized encoding. Magically, as in all cases, Yao has already done this for us. Yao and Ishai and Kushalevitz and Benny has already done this work. So yeah, this you can put it in and do the same PPE trick, and that will work. And then that's it. Here's how you're going to construct functional encryption scheme. First step, which is natural, is that I only have like bilinear PHFE, which is through bilinear maps, which computes this degree 2.5 polynomials. I want to be able to compute some circuit on the message M. So I don't have that power to compute it directly. So what I do, I compute a PRE of this, pseudo-random preprocessed randomized encoding of this message, and I get this P and S. This part is sublinear time because PPE is sublinear time. Then I'm going to just encrypt this P and S. And P is public because PHFE only hides the secret part of the input. That doesn't do anything with the public part of the input. But public part of the input is kosher in the sense that it doesn't leak anything. How do you generate a key for some circuit C? You're going to generate a PHFE key for the circuit, which evaluates PRE.eval. As we saw before, this is degree 2.5 because it needs to be, otherwise PHFE cannot give you the key for this. So that's the secret key. And then once you have this, you can compute the randomized encoding and be happy. Okay. Overall, this is sublinear time because every step, this is sublinear time, and PHFE is just, when you encode something, it's just very linear time in the length of the input. And that's it. You ask Abhishek to convert this to IO, and that's it. Okay, I have like 7 minutes, but let me step back and talk about future directions. So, really this is, we have been studying IO for a long time. This is 2025, and I guess the first construction paper was 2013, so it has been like good 12 years. But we actually know very little. There's only one construction which somehow, contrived construction, which somehow kind of works and give you IO from well-studied assumption, but that's the only one, right? It's very hard to even come up with a slightly different framework or slightly different set of assumptions. Kind of all stuck at like these three kind of assumptions: a local assumption, then like a coding assumption, and then bilinear maps. So coming up with new ways of construct IO, that's a major problem. I'm really hoping that this workshop that we have on obfuscation kind of hopefully spawns new directions for that. And then, yeah, there are other questions. We don't care about efficiency. We are theoreticians. But I've talked to people. They would want to have practical IO scheme, even if it's heuristic. Yeah, that's a great question, and it will really have impact. Hopefully, we can come up with something practical and let the community sit over with that. And the highly recursive use of primitives. FA is still possibly implementable, but not IO. And then, yeah, post-quantum IO. This is broken through bilinear maps. And just to be very concrete, just to focus on the scope of this talk, which is from well-founded assumptions, well-studied assumptions, let me ask you, can you remove local assumptions? Right, PRGs in NC0. And yeah, it seems hard. Although I have to, shout out for this work of Seyon, who's in the audience, I think Nikon and Vinod, which actually showed that you can replace Goldreich PRGs with sparse LPN. Depending on whether you believe sparse LPN or more or PRGs, that's a different question. But yeah, this is a really solid contribution because you don't have to rely on like algebraic. This is more like noisy, in the realm of noisy linear algebra.
But it's still local, right?
It's still local. I'm not getting rid with local. It's still constraint satisfaction, but still, at least it's slightly different. Just the flavor is different. I will not describe the high-level idea, but one could hope that maybe sparse LPN is as hard as LPN. We don't know a conclusive answer for this question. If that happens, then that's going to give you a pathway to get the construction from LPN and PRGs, LPN and bilinear maps. But yeah, there's some initial work on this. We're still very, very far. So that's a great question. I mean, in its own right, forget about I/O. And-
You don't mean strictly harder, at least as hard.
I mean, in black box complexity sense, hard.
I mean, at least it's not.
At least as hard.
Because you can always add more noise and make it more sparse, I guess.
We can add more noise to.
Or in one
So-
direction, is there an easy reduction? In one
No, actually, we don't know either,
Oh,
which is really surprising. I mean, in lattices, it's true because so-called sparse LWE is going to be broken if you had an LWE article because of worst case, average case, works that you guys did, right? The worst case, average case reductions on lattices. This is not known for LPN. And finally, I want to think more about post-quantum I/O. It's like really frustrating. But I have to say the reason I'm excited about this is that there is a whole family of work that has been coming out, not only in like heuristic candidates and new assumptions on constructing post-quantum I/O. The reason it's like also exciting is because it's giving out different kinds of flavors of assumptions, which seem really useful to study, just from cryptanalytic point of view, but also because I believe that they might be useful beyond obfuscation. And that's really, I mean, the reason why this is so exciting. Hoping that, the other workshop covers a bit of this. Yeah. So that's all I had to say. If there are questions, I can take them now.
These assumptions, do they all give us like bilinear or multilinear maps? Sort of basically the question is, can we get all the other nice things you can get from bilinear maps? Also,
Not
any of these work out?
Not quite. The way they work is that they start with some sort of FHE scheme. And then now you need to decrypt things. So you give heuristics, which allow you secure decryption of FHE for the right computation. So that's what's going on. So far, I'm not, it falls short of bilinear map because in bilinear map, there's no restriction on you. You can compute like pretty much every degree to computation. The scope of these assumptions is really specific to computations that we are doing. So they are more enforcement related. Kabir?
So about the efficient IO stuff, are there like some very strong heuristic assumptions we can make that you probably don't oversee?
I'm saying give me a candidate. So
I'm asking in the context of your PRO construction paper.
again, PRO is also recursive. It uses FE to IO. I'm just saying it's something direct, not going by FE. I mean, FE is great, it lets you prove stuff, but we probably want to abandon non-black box use of things. Okay. Sounds like either I was too clear or too unclear. But thank you for letting me.
Reception.